I'm Jim Tommaney, CTO here at Calpont. This is Fernanda Foertter. She's a number of things, but she's a self-professed data geek with Genus, a company responsible for genomic aid to agriculture. Our agenda, we do have a new release of our product coming out we're going to talk through. The focus of today's talk is Genus' use of technology to deliver differential capabilities for their company. Fernanda, scientific programmer, Genus, myself. So a little bit about the InfiniDB technology. So our corporate offices, we also have distributors in Japan and Europe. We are a scale-out MPP architecture. Columnar storage underneath it delivers performance and an ease-of-use experience. We have a commercial open core model, so you can use the software in a number of different methods. And our .com and .org representation. A view of our customers. So this is our commercial product, customers in production. We have additional customers using our open source component. We don't have all of those listed here. So there's an interesting story here. So the same day we first talked to Genus, this was, I believe, something like April of last year, we also were talking to Warner Music Group. And so I went from having a conversation with Warner Music Group about Cody Simpson and Justin Bieber and who was the hot artist and how are you going to figure out the demographics on how people are using these or relating to these artists. And then literally 5 minutes later we're talking about genomics, genotyping, learning what SNPs are, and things like that. Some additional company representations. We do have a good presence within the web analytics space as well. Some retail, some telecom. InfiniDB, scalable, fast, simple. So what does that mean? So from the outside, we're just a database. So we look like a database. You ask questions of it by SQL. We are a MySQL storage engine, so it's familiar connectivity with MySQL storage engine. So it uses the same JDBC drivers. So any tool that connects to MySQL will also connect to us. Underneath the covers, we are a scale-out architecture that delivers game-changing performance. So from the outside, it's just a database with all the easy use you expect. Underneath the covers, we have all the technology to deliver performance at scale. So where do we fit in the world of technologies out there? So certainly there are general-purpose databases. There are technologies highly optimized for entity lookup, entity access, even against very large data scales. Then there's technologies are specifically designed and optimized for analytic workloads, finding patterns out of millions or billions of rows of data, even if the data set is billions or trillions of rows. So engineer for large queries for ad hoc flexibility. So with our columnar architecture, you can actually access or search based on any combination of filters and get a very flat, predictable performance curve. So that makes it a good ease-of-use experience with the product. But definitely analytics and not OLTP, online transaction processing. Our scalable, fast, simple. We'll talk through the details of that. So there's 2 technologies that come into play for our experience. It's one, certainly the scale-out capabilities delivered with our MapReduce distribution of work. Then we actually have a combination of technologies around I/O that together deliver a transformational experience. One of them is certainly the columnar storage. We are a pure columnar database. So we actually do store each column out of a record is stored separately. It can be referenced separately. And that allows for about an order of magnitude less I/O for analytics style queries. So just a quick graphic representing our MapReduce operation. Internally, we actually map all the familiar SQL structures against our MapReduce operation. So the joins, subqueries, group bys, those sorts of expressions, as well as you can craft your own user-defined functions that will run our fully MapReduce manner. The experience is different with us around the use of the subqueries. We actually have a high-performance experience with subqueries. You can use subqueries to your heart's content within our engine. That's a different experience with the MySQL engine. And in terms of the distribution of work, basically the use module will distribute the work across a large number of very small jobs. We'll create thousands of very small jobs in support of a given query. send the results out to a distributed thread pool that's across a cluster of servers, and return the results to a central location. And so the user module is the reduced phase, handles the reduced phase, and the performance module handles the bulk processing. So just to clarify a little bit in terms of our MapReduce, so we're not a Hadoop style or a Hadoop architecture. Internally, we have our own MapReduce architecture that's custom-built C++ applications that has the linear scalability characteristics of Hadoop and the ability to allow individual threads to operate on subsections of the workload independently without coordinating with other threads. And so those two parts are in place, but we have a different latency experience. We're much faster, and we don't have the same idea where jobs can take minutes to get going. The jobs are a small fraction of a second. So it's our custom-built, highly optimized framework. So we talked about our I/O efficiency. There's a couple things in place. So certainly vertical partitioning. That's just the column storage that basically divides the database up into vertical pieces. Horizontal partitioning. Internally, as the data comes in, we'll actually map that to ranges of rows automatically. We'll track minimum and maximum values associated with these ranges of rows and use that for partition elimination or I/O elimination. The next term is something called just-in-time materialization. That's something that's unique to the pure column databases. We'll actually, if you can imagine an SQL statement that's got a combination of filters that narrow the data set in the funnel. We'll actually apply those filters in sequence and only do the I/O required for each individual step as we need to. When we do the final project of the result of the rows for the analysis, we'll just do the minimum rows required there. Some additional techniques for efficient I/O. Sooner or later, we do have to do I/O, whether it's from memory or from disk. We've got some additional efficiencies there. We have columnar compression. You can imagine columnar data values. Columnar data has similar values within each column stored, so we get tremendous compression ratios. 6x, 8x, 10x, or more are possible. You can sort of scale our scale-out architecture. You can scale to run in memory. We have a number of customers doing that operation. Our compression algorithms, a couple things about those. We've actually selected compression algorithms designed to accelerate reach from disk rather than be a performance penalty. So they actually run faster with compression in place. And then we avoid random I/O. We have no indexes in our engineering group, so we don't do any random I/O, random access to the data. So all that put together, what that allows for is the vertical partition, horizontal partition, compression, and how we distribute the data as it comes in, how we distribute the workload as it comes in. Basically makes for a simple and easy user experience. It just allows people to create tables, load data, and then run queries, run their analytics. And the result is a very consistent and predictable performance curve as they're executing their analytics. Scalable, fast, simple. So we do have an announcement today. We have our InfiniDB 3 is coming out that allows for additional parallel capabilities, parallel load capabilities. There'll be an Amazon machine image. I encourage everybody to take a look. We'll turn this over to Fernanda. And the good news is that we won't be hearing any more about Cody Simpson or Justin Bieber.
Good afternoon, everyone. And we're not going to be hearing about ads either. I'm going to tell you a story about Farmer Ben and how Farmer Ben went from farming all the way to get a PhD in genetics and then hired me to help him with his data evolution. I work for a company named Genus. There are two sides to our company. On the porcine side, essentially, we're growing your bacon, right? Anything that you buy that's a pork product. About the last I heard, is about 70% of the pork you buy has some sort of our genetics in it along the way, in the U.S. at least. In Europe, it's about the same, if not a little higher. On the ABS side, so you have both beef and dairy. And on that side, the genetics isn't as sophisticated, as controlled by the USDA, but we're starting on that front too with some genome sequencing. So Farmer Ben used to do just regular old farming. You get your handsomest little piggy and you marry to Miss Piggy and you get whatever product it is you need. And if it has some, it's been healthy, it hasn't had any disease, Farmer Ben picks those two. What Genus has then done is This is not any creepy genetic engineering or anything like that. Genus just at the beginning, or at least on the PSC side, is to just then measure phenotypes. So phenotypes could be something like the yield in the meat, or the litter size, or some sort of measure of quality in the meat. And then it would put all of that together in some sort of genetic evaluation, and it would create a breeding value that then farms would say, I want to use the semen. We're not going to talk about Justin Bieber. We're going to talk a little bit about semen. If anybody gets a little red in the face, I apologize. But our product is, I'm sorry to say, semen. So a farm would call and say, I would like this specific pig for whatever quality the farm is looking for. If it was, for example, a Chinese product, Chinese customers prefer a stronger meat. So, we would give them something that has a little bit stronger. You get the idea. So here's an example of a phenotype, for example, meat quality. The meat on the right has not lost a lot of its liquid. The meat on the nice piece of steak on the left has lost a lot of its liquid. If the customer, go to the supermarket and you look at the one on the left, you might not buy it because you might think, well, that one is just a little old. Actually, it has nothing to do, this is all the same age. It's just to do with some qualities in the protein itself that has caused it to lose its higher content of liquid and color. So Farmer Ben gets a little more sophisticated. He's now collecting all these phenotypes, and he's creating these evaluations. Way back when, these evaluations were either done by hand or Excel spreadsheets, and Farmer Ben's all excited with his new computer skills. And he's able to select for growth, and he took all the fat little piggies out of the herd, and now we have lean, handsome little piggies that yield a lot of meat. And you can see that Farmer Ben's doing a good job, because our parents, at least my parents' generation, they used to say pork is fatty. Pork is no longer fatty. What's pork today? The other white meat. There's the proof. Well, except Farmer Ben is now selecting for all these high yield, carcass yield meat, and it turns out that every time Farmer Ben tries to move his little piggies from the farm to, say, the slaughterhouse, or from a pen to a growth finisher, little piggies get all stressed out and they kind of croak. Literally, they just kind of, I'm stressed, and they die. And that's not good. So it turns out that Farmer Ben goes to the university and decides he's going to learn a little bit about genetics. And he found the halothane gene. Well, he didn't specifically, but you get the idea. And he found the halothane gene, and the halothane gene is exactly that. So it used to be that literally the only way you can figure it out if a pig is going to be stressed out is you have all these vets with laughing gas, putting tiny little masks on tiny little piggies, and hearing their heartbeat. And if it went up, they said, we're not going to breed that pig. Well, things got more sophisticated in genetics. We found this gene, and we figured out it triggers hyperthermia, and it's also associated with high carcass. So if you are selecting your pigs for high carcass, well, you're selecting for this gene, and you're selecting for these pigs to perhaps have this gene. And it also ends up yielding poor meat quality, especially because the pigs are so stressed. Stress hormones end up causing poor meat quality. And so Farmer Ben goes and gets his PhD in genetics, and he finds a whole bunch of other genes that have to do with litter sizes and mortality and all sorts of other great things that we care for in the product. And Farmer Ben finds himself in a real dilemma because his data is growing. In the beginning, when PIC started looking at genes, we were talking about maybe a handful of SNPs, single nucleotide polymorphisms, which are essentially chunks of genes, not necessarily whole genes, it could be, but chunks of genes. And we were maybe at 300 or so. And then suddenly, that technology got real cheap, real fast, and you have thousands and thousands of pigs in a herd. You can see yourself in the data deluge very, very fast. And Farmer Ben's not stupid. He knows that to make associations with these genes, he needs to measure more things and get more phenotypes. And there's literally a vault somewhere. It's kind of creepy in a sense, but there's a vault full of refrigerators and little piggy tail samples, or some sort of tissue sample we've gathered from the pig, from every pig that's ever been born in any of our farms and or farm customers that we have. So we have tissue that we can measure, say phenotypes that come later on. We can measure those phenotypes if we learn what they are, the measurement that they are, or the herds have gotten bigger over the years. So now farmer bench genetic evaluation is not by site, it's not just by phenotype. Now we're combining this genetic information to create that breeding value. We weigh it with some sort of economic weight. Remember I was telling you about Chinese prefer darker meat, so I can weigh it and say, hey, for the Chinese market, this is more important to them. And now I create an index, and each pig has an index depending on what qualities it is we're looking for. This could be something as simple as, health, pigs that are susceptible to pneumonia or some sort of other disease that we can breed out of the herd, so we won't have to use, for example, medication, antibiotics, or whatever it is that they're susceptible for. We can breed those guys out and create a healthier herd, healthier product for the customer, healthier product all around, cheaper product, etc. So now there's a data pipeline that we have to construct, and things are just sort of ballooning in data sizes. We have SNP data and the thousands of SNPs. We have now sequence data because sequencing has gotten so cheap. We have phenotype data that we're gathering on thousands of animals and hundreds of measurements, whatever those measurements may be. And then there's research on top of that that's generating data that we might want to use. And all of that goes into this one giant machine of computers that quickly gets very complicated. We're generating even more and more and more data. So I realized that when we were growing in genetic data, these scientists were literally poor guys, and girls. They were using single text files, giant gigabyte-sized text files, and so if they wanted to find out what happened 10 years ago or 5 years ago in genetic information, they'd have to go through several text files. And so we had this one data analyst whose job had digressed to get people data files. He was extremely versed in Perl and bioinformatics, but essentially his job had come down to, I need these animals from this farm for this period with these SNPs. And that's all he did 24/7. And I said, this is inefficient. We need to find a way. And I'm young and stupid. And I said, Facebook has solved it. Google has solved this problem. I can solve this problem. I knew nothing about databases. But I said, I'm young and stupid. So I went for it and I delved into it. Another example of the data is just getting giant. We had about 4 terabytes worth of drives everywhere in data when I joined the company in 2009. 2010, you can see it's just a little bit over 2.5 terabytes. We installed this parallel NFS system called Panasys. Within 2 years, we were up to 30. Giant data, being generated genetically. Now we're over 114 terabytes worth of storage space, and it's filling in fast. So I said, okay, I'm young and stupid, I'm going to do this, I'm going to solve it, I'm going to create a genotyping database where all our genotyping information, all of our sequence information is going to go into this database, and they're going to be able to query it for whatever it is that they want. And we had already tried this in Oracle. In fact, this information was already in an Oracle database that was being used in financials. We had it available, and so therefore they were trying to use it. It just wasn't the right data to go into Oracle. And Oracle was getting very big. The licensing requirements were getting big. All that other stuff everything with Oracle was getting very expensive. So I said, I'm going to do this the open source way. I'm going to do this for free. I'm going to solve all your problems. And I needed something that could get accumulated chip data that wasn't, that avoided the difficulty in searching through it, not having multiple files. I could also put in next generation sequencing data because it's essentially the same data. I mean, it looks the same, it's just less of it. Lots of animals could fit in it, and there are other projects that also wanted to look at the data, so I needed something that multiple parties could connect to. So some considerations that are, storing large data, I needed it to be scalable. I needed it to be an alternative to Oracle. We had tried Oracle, and it just didn't fit the data right. I wanted it to minimally impact infrastructure. On top of all of this, I said, I'm going to use it with existing hardware. I thought I was crazy at one point, and I think everybody else did too. And then I said it needed to be easy for scientists to use. I couldn't do something that was too difficult that would require them changing significantly what it is that they were doing already at the moment. So I went outside there and I said, somebody's got to have solved this, right? And I looked for humans have been doing genotyping for a long time. We're not new to this. And there's nothing out there. Essentially, all the human research is done with text files. That's it, standalone text files. So I started looking at all sorts of other options. I looked at, I started with Cassandra, but the issue was that there's so much sharding in Cassandra that we'd have to have very specialized hardware and add to our current infrastructure to be able to make this run. I looked at, key pair, value pair, databases. I looked at the stuff that Google has. I looked at all of those things. And either they were too difficult for my scientists to be able to do, or I'd have to do, I even looked at object-oriented databases. And then I'd have to do all this development for it, which would have taken a long time. Or we were a Linux shop, we had a Linux cluster. I didn't want to do something that was based on Windows, for example, SQL Server. So I looked at all of these, and then at one point, one more Google search led me to Calpont. So I downloaded that open source version or open core version that they have, and I started out playing with that, and immediately I figured out that this is perfect because they have a MySQL connector. In the back end, there are NoSQL, so they're a columnar database, and this is exactly what I needed. And the lesson here for me was I realized at some point that not all databases are created equal. So if I said to you, I need a vehicle, this is a vehicle, and it's very sense of the word, but I could be thinking about this, and many in the audience could be thinking about any number of these, right? So a database may be a vehicle for your data, but without you understanding what it is that you're going to use that vehicle for, and who's using that vehicle, and how they're using that vehicle, and what your data looks like, then you can choose whatever, and you're still going to be disappointed because you didn't fit the data to the database, to the usage patterns, and everything else that you had. So this is what our genomic data looks like. It's not very difficult. Essentially, I have samples. They match up to animals. The samples can be low-density genotypes. They can be high-density genotypes. They can be sequenced. They can be phenotypes. But I have an animal ID. I have some data about what it is that they have. And then there's some other extra things that come with genetic or with the genotype files that give you some sense about the quality of the genotype calls. And all it really ends up looking like for the scientist is this. I have animals on one side of the spreadsheet, right? And I have SNPs, and I have 65,000 columns for example, for a high-density genotype. And if I have sequence, then I have a lot more columns than that. On the cattle side, you're looking at 800,000 SNP chip. For humans, you're looking at, I think they have over 1 million SNPs for their high-density SNP panels. And all my users want to do is they want to go down one of these SNPs and say, give me all the animals that have allele 1 for SNP 1 and allele 2 for SNP 36,765 and phenotype blue. And they want to be able to, hone into that data. And essentially what they were doing with Oracle is they would house all that data with, say, a typical RDBMS. They would house it there, and then they would do this giant data dump because you can't do those sorts of queries in that sort of database, right? The more you hone in, the bigger your queries get, the longer the times. And so they would do this giant data dump and then create script files to get the data that they wanted. And what about if I wanted to do cohorts? What if I want to find out not only the pigs that have certain SNPs on, and they were born on a certain day, and they have a certain phenotype, but they were born on a certain farm on another day. I mean, now we're talking about the ability to do different science. I can cater it to a specific farm, and then look at a disease susceptibility to a farm in Iowa in the month of March. This is something that's completely foreign to the ability, to before. Before they were just looking for SNPs that had some sort of association in a giant herd. Now they're saying, what's affecting a farm in China? What's affecting a farm in Germany in this specific month? What is it about this month? Is there something else? Is there a farm next door to it that had the same problem? Is there something specific to that farm? This is completely foreign now, and now scientists are asking other questions because data is no longer the issue. How to access the data is no longer the issue. Now it's just a matter of just trying to get things out of that data. Column database then certainly makes the most sense. I'm honing down specific items. And how he mentioned compression, a lot of these data sets, if I'm talking about farm, my column for farm is just very compressed because there's just rows and rows and rows of the same farm because it's thousands of animals, so that gets compressed real easy. And it makes complete sense. You don't have to touch every column when you're searching, and you can go exactly to the column that you have, that you need. The other thing that's great about, that I learned later on in talking to the engineers at Calpont, is that they have these chunks of columns. So, in my idea before being an HPC programmer, scientific programmer, when I think of parallelism, I think I'm going to break the problem down, I'm going to go down that problem, and I'm going to spread it in my CPUs or my cores or in nodes, and I'm going to go down that column. Well, the beauty of this is that they have chunks of columns that are identical in size. So when they break down and parallelize that problem, I don't have to have 65,000 columns. I can have, one column for SNPs, but they're going down chunks and they're parallelizing these chunks as they're searching for it, which is the same thing. I mean, you get the same thing, but you're still getting the data. You don't have to complicate your schema in that sense. Anyway, so that is a representation of that. You have these chunks of columns. Each core then takes care of the chunks, which would be completely different in a row scenario because, in a row database, you have to go to each row and touch each section, and it wouldn't be very ideal for this kind of data. So, like I was saying, these sorts of queries that you have very, very long, you're trying to narrow down your focus to your data. You have this very large terabyte size or tens of terabytes of data, and you're trying to narrow down. The more complicated, it's reverse thinking, but the more complicated your query, the quicker it gets to your answer. And the beauty too of Calpont, I found out, is that they push a lot of it to cache. So if let's say a scientist is trying to look for those cohorts, right, to be able to say, I want to find out about these farms. Cohorts meaning, essentially, the experiment, the same people, the same things, the same items in the experiment. If he wants to look for specific patterns, he can keep searching and searching and searching over, because now that data has been pushed up to cache, and now his query is getting faster because it's moved away from I/O. And now my one single person that used to be great at bioinformatics and was subjected to just looking for data, now he's helping the scientists actually look for data. Again, the scientists have direct access to that data. For our data set, we got compression nearly 75% for most of our stuff. We're at least 15 times faster than a regular RDBMS. It can scale. This database can scale to 100 terabytes. We're not even close, but I'm not even worried. We've seen no penalty at all in putting the data into the database. And it costs a fraction for the commercial version, which you get some benefits in parallelism. It costs a fraction of what it would have been if we had just upgraded the licensing and the hardware with Foertter. And now it's led to new science. So, I said some animals have low density genotype and some animals have sequence data. Well, now I can say, well, if I have sequence data for mom and I have sequence data for dad and I have low density genotype for the kids, well, why can't I infer the high density stuff for the kids? I know who the parents are. I have good quality genotypes. I have sequence data, which is essentially their whole genome. Why can't I infer to that? Now it's led for us, instead of paying $150 to do 60,000 K genotypes, we're paying $15 for a tiny little chip that gives us enough information genetically to be able to then fill in the gaps and infer what 60,000 would be, infer what the whole sequence might be on a specific animal. I mean, that's, again, you can see the data size growth in here, but that's huge savings in cash for when you have margins that say, for a farm, for example, sometimes the margin per head could be $5, $10. Now we're saving the customer's money. We're saving our money to be able to do even bigger research. So my caution to you is that data multiplies in a big way, and you have to understand your data, you have to understand who your users are, and you have to understand all of that to go into one specific package. Don't think that because Hadoop is a new kid on a block, you should necessarily have to use that because. Understand what Hadoop is, understand what your data is, understand what your users are doing. And so, like I said, have a deep understanding of the scientific data and the problems being solved, have a good understanding of the data access pattern, and don't solve everything. You're not going to be able to solve everything. I try to aim to solve for about 80% of the cases. There's 20% of the cases where And actually, I ended up solving 100% of the problem because even the other 20%, it's still faster than what I had before. So I ended up solving 100% of the issues that they had before with the data axis. And I used a combination of software, hardware, and knowledge to improve performance. I had an existing cluster. I had a parallel NFS system. I was able to install this on a single node. I was able to just give it some cores. You know, I got licensing for X number of cores. I didn't have to add any extra hardware. I didn't have to add any complexity. It was already there. And think outside of the vendor's box. My lesson in this was they're selling for analytics. They didn't even know that our data existed out there and there was a need for this. And I said, you know, this looks like it fits log files. I just happen to be a computer person and I understand that it looks like log files. So, you know, why can't I put your data in here? And it's like, well, you know, why don't you give it a try? And it worked out okay. So think outside of the vendor's box. Don't just look at a vendor that says they're selling a database for analytics and not think that it doesn't fit your science. And I also took the lead, and I was, you know, like I said, I was young and stupid, so I took the lead and I said to the users, I can solve this, and I can do it in a way that you'll be able to do your science in a better way. And it was kind of scary, but Calpont helped me out with that in a big way.